So let's start with introducing another speaker. So it's Sandro Montanari. He's the director of product at company Inpher, who is, by the way, a sponsor of today's apero. And I hope you're gonna to stay after this, because after each event we have apero with a wine selection, thanks to direct help from Sandro. And he's gonna to tell a little bit more about company Inpher, but we pair this company with also the previous talk, because they are basically dealing with the world in Europe after GDPR. And the career of Sandro is something really interesting, because he started as a master in science at EPFL, specialist in robotics and intelligent systems. And he was also doing a lot of management already at that time. And as I found on his LinkedIn, he was organizing some radio transmissions and concerts with up to 1,500 people. So I know that it requires a lot of time and talent and preparations to do these things. After this, he was actually working in Assyriel and Fribourg, and you can check this company. They're doing pretty cool machines. They are producing these machines like for operating with tiny particles and putting them on places like tiny magnets or screws for computers. Then he moved to Swisscom for over 5 years. And this is something what I encourage you to talk with him, because he got a position which is really nice for students. It was during the studies, yes, or after?
Yeah, that's the traineeship from Swisscom, yeah.
So traineeship, and you can apply for this. You have very interesting interview, as I understand, which was more like how intelligent person you are, let's say to make a presentation in half an hour from materials you have available in the room. So it sounds really interesting. You have plenty of possibilities on these positions, and after this he stayed in Swisscom for 5 years on different positions like project manager, product owner, cloud development engineer. And right now he started his new challenge in company Inpher, which is a startup located here in Lausanne and in New York. So more about this, Sandro will present.
Thank you, Pawel. Hello, good evening. Thank you for coming out. I'm really happy to see so many people have chosen to come today, and I'm really proud to be able to speak to you today. Thank you also to Michel for the introduction. I'm really happy about the references. This is gonna work well. So cool. Let's start. What I want to show you today, briefly in an outline here, I want to mention the team, our company, what we do or who we are, where we are, and get over our value proposition. And then the main part of the talk, I want to focus on our two core products. One is called EXOR and one is called TFHE, where I really want to make sure that I get over the working principles of this technology and how it can help you in your everyday life and make actually your lives better. I'm going to end with a few communications. But before we get into that, I want to make a little digression, and I want to start with a little side remark. Maybe some of you know this. This is the cast of the HBO TV show called Silicon Valley, which is about these 5 guys who are young engineers, and they start out and they want to do a startup. Basically, they have a lot of problems. They don't really know how it goes. One of the biggest problems, obviously, is legal problems. And they don't know how to face this because they're engineers. They never had to do this. They have trouble with investors. They have a hard time to find office spaces. They have trouble to find new recruits for their company. And obviously, they also have drama in their company. And the reason I'm mentioning this is that these guys go through a lot of stuff, and it makes up a whole TV series. When you're a real-life startup, you also go through a lot of stuff. And the stuff they went through, we all went through that as well. We have these legal problems. We have the problems with investors. We have problems with office spaces. We have problems with hiring people. And all the things that come up in a TV series like this, you can have in real life as well. It's your own private TV series. So the point I want to get across is a little bit of advertising for me, as having worked in big corporations up to now. Having done the leap to work in a startup has been a really enriching thing to do, and you can make your life become almost a TV series. For the little side digression. Let's dive into the more applied stuff. So yes, we are a startup. This is basically us and our team right now. It was founded or co-founded actually by an EPFL professor, Dimitar Cechev. He's sitting right here in the audience with another co-founder. We've managed now to make this first bigger leap, that we come from a small startup into a bigger startup where we raised our Series A. This round is signed. We'll be announcing this in the next 1 or 2 weeks. You will be able to read about us in the media, I hope. The things we do, they focus, they're a mix of research and product development. And the way, or the field we're in is basically in cryptography and in machine learning, which is we apply on. Like in the TV series, we have pivoted. We didn't know from the beginning what the product should really be, and it's been pivoted. And also like in the TV series, our stuff works with blockchain or can work with blockchain, so we're really trendy in the technology space. We also know blockchain. Cool. Final remark, we have an office in Lausanne and an office in New York City, which is a cool place to go, and you have exchange with cool people over there, so that's fun. Okay, let's dive into the real stuff. I want to tell you our value proposition. Whenever you work with data, you're faced with this kind of big problem between security and utility, meaning you have your data, but in order to store it somewhere and to have it secure, you need to kind of encrypt it or have it secured in some kind of way. But as long as you have encrypted, you can't really work on it because it's encrypted, and you need to decrypt it before you can use it. So you have this gap or this paradigm between security and utility. But what you really want to do is have both. So this is our value proposition. We want to be the ones bridging the gap, or actually eliminating the gap between security and utility, and making sure you can use your data in a secure way. This is the thing we want to do. So let me tell you how we do that currently. We have 2 products that we're using. One is called EXOR. It is a product based on what we know as multi-party computation. We'll get into that more in detail. It is our commercial product, the one we sell and also the one we use to raise our money on. Then there's a second product, which is called TFHE, and it's based on fully homomorphic encryption. It is our open source product, which is an open source contribution that you can see on GitHub. I'm going to go now for the rest of this talk, or the biggest part of this talk, through these 2 products and try to make you understand how they work and what they actually do. Let's start with EXOR. So EXOR is a product, well, I think this slide doesn't really do it justice. It doesn't explain it well. What I'm going to do is I'm going to try the old-fashioned way, using the chalk, to explain this. I want to make sure to really get this message across. Little side remark, I used to be a student here in this classroom, and now I'm holding the chalk. Feels pretty good. So I want to set the premise. First premise would be you have different entities. Let's say 3 entities. Entity A, Entity B, Entity C. All these 3 different entities, they have data in a data set. Thank you. They all have their data. And within every entity, or let's call them company, there's an analyst sitting with his data and doing machine learning on these data sets. Now, this is the status as it is. But all these analysts, they know from each other that they can improve their model if they could only get access to the other guy's data. So this guy knows that for these 2 data sets, this guy knows that for the other 2 data sets, and actually if they could just collaborate, they would all be happier. But there's difficulties to collaborating. Once, you don't really want to give away data. Another difficulty could be GDPR. So there's stones in your way for this collaboration. And physically, you can imagine like barriers between these entities, so they can't collaborate. Now this is where we come into play. You start using Inpher, or actually EXOR. Let's maybe focus on this analyst right here. If these three entities decide to be using EXOR, what this analyst here would see is first metadata from the three data sets. Only metadata, never data. We don't have the right to touch data, only metadata. So he would, for example, see table A having header 1, header 2, header 3, like this, but no data. He would also see the same thing from data set 2, header 1, header 2, header 3, and so on, no data, same thing from data set C. Now, with this information, he kind of knows what the data sets contain. Headers, they can be name, age, where the person lives, things like that, metadata, information about the content. Now, what he wants to do is actually build a machine learning model. So let's take a simple example. Let's say he wants to do a linear regression. He can then say, he can choose what he wants to do. He would say, I want to compute a function, linear regression, and pick actually features from all the data sets he wants to use. Let's say he uses alpha times header 1 from dataset A plus beta times header 2 from dataset C plus gamma times header 4 from dataset B, and so on. Doesn't really matter, just a function. Now, this is the function everyone sees. Everyone knows this is what we want to compute. Now, what we also know is the number of columns, the number of rows, and the number of iterations to compute this function. And obviously, we know the function because this is public. So, this is public information and the headers are public information. That's all that is public. The data, keep in mind, stays in these three data sets. No data has been exchanged. All everyone knows is this. So this is submitted to our EXOR engine. Knowing the function and the dimensions of the data, we can actually pre-compute every execution step of the linear regression model. So we know in advance every step that the model needs to compute without having the data. We just know what needs to be done mathematically. So we do it mathematically. We compute 3 executables, individual executables. So a program for a computer to run. We send one executable here, one here, and one here. Now what happens is that locally this program gets executed on the local data set. Locally. Once they've gone through that, what they will do is reveal the final answer. Final answer. Answer here being, since we do linear regression, it's just going to be a vector with alpha, beta, gamma, and so on, the values we had here in our linear regression. Recap. All we publicly know, the function and the dimensions of the data, plus the answer. No data. We use the data to train a model locally. The data never leaves the local place. The answer gets revealed to everyone and everyone profits. So the 3 guys that wanted to work together with them, they can, without having to reveal their data. Obviously, for the computation to work, the 3 data sets need to exchange something. They don't exchange the data, they exchange random numbers. That, if done well, result in an answer. Now, this is the next step. Let's look at this. So first I want to reiterate, and I want to let my old friend Gandalf do it. It's like magic, so Gandalf. We use someone's data without having access to it, but still get the use from it. This is kind of the premise you have to set your mind to. Now you don't trust Gandalf, so we're going to go through an example. We're going to take a simpler function. not linear regression. We're going to take just a very simple function, summation, plus. Let's say we want to add two numbers, and we do it in this kind of way I described there. We want to add the number 6 and the number 13. But we're not going to reveal those numbers. They're secret. So we secret share them. First, the number 6. Player 1 gets 18, player 2 gets minus 40, and player 3 gets 28, as an example. Note that if you sum these three numbers up, 18 plus minus 40 plus 28, you get 6. But no player individually can really know what the 6 is. Only if the 3 would collude, would collaborate, they would know. Because if the 3 of them show it, then it's known. Same thing for the number 13. You secret share this one. And finally, you get a result. Now, observe. We said we distribute the compiled program and execute it locally. Here, the compiled program, all it does is summation. So if you look at this closely, do you see this? Yes. If we sum it here, 18 plus 3 is 21, local summation. Minus 40 plus 27 is minus 13, local summation. Here again, local summation. But now, summation globally over the 3, you get 19, which is the result. This also works for linear combination of numbers, like so, which doesn't change anything in the result or in the mathematics. And what we are able to do is have correct results for a function that we want to compute, distributed and private. It also works if parties collude. Imagine like player 1 and player 2 would collude, then they still don't know the secret share of the third party because it's not known to them. You can't find it out. And so we keep the privacy of every data set, but are able to mask it with random numbers. Just a quick remark, this doesn't work for multiplication just like this. It also works, but you need a little more mathematical detail. I'm not going to go through that in this presentation. The time is too short. We can do that at the end if you still have questions. But it works. So now, why? Why go through this? Why do all of this? Let's see some use cases, some applications where we have customers actually really using that. And I want to start out with a use case in predictive maintenance or anomaly detection. We have two clients using that. One is the French company Thales, and the other are the European Space Agency, who both use anomaly detection or predictive maintenance. And Thales has composed a video kind of showcasing this use case, which I want to share with you. I think there's no sound here, but the sound is just a little music, so it shouldn't matter actually. I'm not sure the use case completely came across. I'm going to quickly summarize. You have Highly sensitive information like mission critical flight data from fighter jets. You don't want to share this data, or you don't want to give away this data. But you want to give away sensor information on your critical systems in the aircraft because you want to have predictive maintenance of your aircraft systems. And if you can collaborate on predictive maintenance on all the aircraft running all over the world, you get better predictive maintenance. So there's a big interest in sharing the inside of the sensor data, but not the mission critical data of the flight, which is highly sensitive in a military application. Same thing for ESA, where it's about satellites and not fighter jets. So this would be the anomaly detection, predictive maintenance use case that we're facing. Let's talk a little bit of the banking sector. This is a use case we did with OCBC Bank in Singapore. OCBC Bank said that, or they want to do credit scoring. They want to know, okay, if you want some credit from us, can we give you this credit, and have predictive models actually computing that for them. And they think that they can increase their credit scoring prediction by taking external data into account. So what they do is they, in this premise, they looked at telco data, so telco operators like Swisscom or like AT&T or these kind of things. They send a lot of bills, and their customers have to pay a lot of bills, and they say that if the customers pay the bills well and on time, this is high, this ranks high as kind of payment mentality. And then the bank would say, if payment mentality is high, I would say that I would give this customer credit because he's very highly paying his bills. And so they run predictive model on creditworthiness together with telco information data. So information outside of their company actually helping their prediction inside the company. And finally, this is where I mentioned Michel and the GDPR part. So yes, we have a lot of customers that face this GDPR issue, typically banks that, for example, have data in, let's say, France, Germany, and Switzerland, and they want to compute on the data on all these three data sets so that they can't export some of this data into one country and then aggregate and compute on all of this. They have to keep this data within the company, otherwise they would violate GDPR regulations. But with our solution, and this is an analysis, I'm sorry, not done by Michel, but by Baker McKenzie.
A better brand there.
Okay. By Baker McKenzie, who actually certified that our solution would not violate GDPR restrictions. So this is one of the escape path Michel mentioned that you can use for GDPR. Okay. Let's sum this up for the EXOR part before we go on. So we have EXOR, which is our signature product, which is the main product we sell. It does computation on distributed data sets. It can help you get access to data sets where as an individual you don't have access, you only get the results of the computations. It runs without the involvement of a trusted third party. We as Inpher, all we do is pre-compute the circuit. We never have access to the data. And the only thing you ever share is input and result, nothing else. Like we saw there, the function, the dimensions, but never the data. And you get correct results with it. Really cool stuff. Yeah. But that's not it. Let's also have a look at the second part. Second part, TFHE, our open source fully homomorphic encryption library, stands for Taurus FHE. So fully homomorphic encryption, and the experts sit here. I'm going to briefly introduce it and give you an overview. What you want to do with homomorphic encryption. So the premise is that you want to run an arbitrary function on secret or private data on a public environment without revealing the function, the data, or the input. So you want to keep whatever you do private. You want to compute on encrypted data, but still get a result without the one hosting your data, which is encrypted, ever seeing anything about it. So the encryption scheme would satisfy this property that you see right here. Imagine you have a message 1 and a message 2. You encrypt these two messages, you get a ciphertext 1, ciphertext 2. Here, C1, does this work? Yeah, C2 and C1. And then you do some kind of operation. The star here stands for some operation. And you do this operation on the ciphertexts. Once you did this operation on the ciphertexts, you decrypt the final result of the operation. You get the same result as if you did it in plain text. Was this understandable? Yeah, some people shake their head, I guess. Whatever you do encrypted is the same thing as you did it in plain text. Simple message. You use this for privacy-preserving computations, and you don't really need to rely on hardware security in these cases. Very, very briefly, what you do in this encryption scheme, this is the DGHV after their inventors' encryption scheme. So you would compute your ciphertext with the following additional numbers. You would set M as being 1 bit of your message. You would take a very big number, K, reasonably big compared to all the rest. You would take your private key. Here I made the example with a 1024-bit key. Make sure this is an odd number. And you take some noise. Noise needs to be smaller than the key. You encrypt with this scheme, and then you get a relatively easy decryption with 2 modulo operations. If you look at this very briefly, the modulo P, what does it do? It eliminates the K part, because you do modulus of basically this thing. And then you're left with basically P plus 2n plus m. Since we said before that the term 2n plus m is relatively small compared to the key size, you can more or less neglect this part for the decryption part. And you're left with more or less P plus a little bit of noise, but it's more or less P. And P always is an odd number. Now you take modulo 2. If this modulo 2 gives you an odd or an even number, you get 1 or 0. And depending on whether your message was 1 or 0, it'll either be odd or even. Was this understandable? Ask me in the end. I'm going to make maybe another description. We can use the blackboard if you need more details. What you need to understand about this is that this is a very reasonably simple encryption scheme that can be used multiple times. So you use this once and you get only 1 bit of information. But this works, since it's fully homomorphic, on many, 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 many bits. And you can chain this. And once you chain this, you get what you call a circuit. This circuit you can compute in plain text, but also you can compute the same circuit with the same Boolean logic in the ciphertext world, so in the encrypted world. This allows you to compute any complexity of function, basically any function you want, in an encrypted way. Of course, there's problems. One of the problems is that since you add noise, this noise accumulates whenever you do a multiplication. So you need to do something against that. Gentry proposed a method against that. Basically, you don't decrypt at the end, but you have intermediate decryptions that help reduce the noise. And since this is relatively complex operations and big numbers, they're time consuming, it uses a lot of CPU power, or basically computation power, and that takes up a lot of your time, and so it's not really practically quick and feasible. Why would you use that? Basically use that if you think that your cloud provider has infrastructure that looks like this, powered by potatoes. I don't know. No, you use this if you think you work on an untrustworthy environment. You use this if you want to do encrypted searches, keep your data encrypted while do searching on it. It has a lot of applications, practical applications in healthcare, for example, genomics, where you do matches, and an encrypted email server. There's many applications you can think of once you actually get familiar with the use. Okay. That was basically the part about our 2 products. Now, just 2-3 final comments. One is Since in the spirit of these meetups, there's also always something we try to give back to the audience and the people here. We want to actually encourage you to use our products. For this, of course, the open source library is, as the name says, open source, and we encourage you to use that as it is. You can also become a contributor on GitHub, which is, of course, very interesting. But we also want to give you the chance to actually try out our commercial product. If you want more details, there's a paper on it. I listed it there. If you would be interested in trying this out, we would give to the people here in the audience and generally all the EPFL affiliates the opportunity to do this on a hosted POC environment that we would provide for you. What we would ask you is kind of a one-page motivation letter where we see what would be your application, where you want to use this, and then we would reserve the right to select maybe the top 3 if we get like 50 applications, because we really can't handle too many of those. We're still small scale. But in general, we really encourage you, and we want to bring this product out and have it used by customers like you, intelligent, smart people who can get really good feedback and who actually want to take advantage of this technology. Please hand in, if you want, to info@inpher.io. The next remark I want to make is this. We just signed the pretty big Series A investment round, and so we're in a comfortable position of being able to scale. If we want to scale, we need people. If you're interested in starting to work at a startup, basically we're looking for all kinds of different talents, be it data scientists, be it just full stack developers, also in marketing or business development. Shoot us an email. We would be delighted to talk to you. I want to leave you with a final remark, which is a quote by Ed Wilder from TensorFlow. He says, "The biggest obstacle to using advanced data analytics and AI isn't base or a skill base or technology. It's plain old access to data. So you can't really reach that data. And we're the ones who try to make you get that data." Thank you.
Really quickly, you mentioned for your TFHP product that you work in the healthcare world are applicable and genomics, genomic medicine. For EXOR, what is your computing speed once the functions have been set up, your metadata has been put in? How fast are you able to turn around the results for your clients?
Speaking about EXOR now, huh?
EXOR.
Okay, yeah. We have first applications, by the way, in healthcare with EXOR. We're talking to customers. In general, once you execute a function in plain text compared to the execution on EXOR, we see a factor of around 15. Factor 1.5 time increase.
And are there any limits to your models? When you're talking genomic data, you're talking we're talking about looking for CMVs or missing variants inside of genomic data.
Yes.
You're talking millions of base pairs long.
Yes.
Do you have any limitations to what your system can?
For now, there are limitations. We've tried. Well, there's two kind of limitations. One is the limitation on actual size of your data. Because right now the algorithm isn't perfectly optimal and we can run into memory problems at a certain point. What we did is a data set with 1 million samples and 100 features, and that worked. But you know, if you scale more and more, at some point you will run into memory problems. But this is being optimized, and we can still optimize there. The other limitation that there is that there's not an infinite number, or not every imaginable algorithm can be computed in such kind of way. I don't want to go into too much details. We can talk bilaterally if you have more details, but not every imaginable algorithm can be done. There's a certain amount of time, and neural nets, yes, they come into play, but not everything can be done.
Again, relating to what kind of function is it? Is it polynomial function? And we know
nonlinear function that you can, because at the end the machine learning algorithm that you can integrate in EXOR depends on the function of the data, right? Is it polynomial?
Yeah, basically the difficulty of the function arises as soon as you start having branching. As soon as you start having branching and you need to evaluate different branches of the function. So imagine if A is greater than B. If you don't know A and you don't know B, you don't know how your algorithm is going to evaluate the rest. And whenever there's going to be another branch, you have to branch again. And your computation or your pre-compiled algorithm actually increases in size at every branch. So algorithms that are complicated to evaluate are branching algorithms. Algorithms that are more simple to evaluate are algebraic algorithms, where you can invert a matrix or something like that. So if it's too branchy, it's going to be difficult to implement. It can still be done, but it's going to take a lot of time and it's going to be complicated. Does that kind of answer your question?
Yes, so for kernel methods, is a good fit, so you don't even actually need the data itself?
I didn't understand.
The kernel methods.
I'm not familiar with kernel methods.
It's where you only need a dot product or a kernel product.
Ah, yes, yes. Yes, yes.
So maybe two quick questions.
Yeah, please.
Can you apply machine learning with homomorphic? With your fully homomorphic?
I guess you can, yeah. It's
Have you done it?
we haven't done it, no. No. It's time consuming. No. But you can.
Some questions. When we train a model, usually it's nice to have a look at the data to find out why it's doing wrong, find out outliers, for example. So you need a system. How could we do that if you don't see the data?
Basically, well, the premise of this working model is that the people who want to collaborate actually want to collaborate. So these people need to make their homework and do data cleansing beforehand. This is something the algorithm, with time, maybe we'll develop such systems that do automated data cleansing and pre-processing, but for now, you need to come with a data set that more or less makes sense. We cannot change machine learning. So everything that you need for a real algorithm to work so the quality of the data needs to be there also to work in our system. We make it preserving the privacy. We don't increase whatever the other machine learning algorithm can't do, we can't magically do. We do the same thing, just privacy preserving.